we're going to talk about thermodynamic phase transitions, particularly in a single species, let's say. And as I was mentioning, the liquid vapor phase transition happens to be one of the most widely known phase transitions, which has been known since prehistoric, let's say, ages, and one of the most studied example also. Okay, so gas, solid liquid, and liquid vapor phase transitions are one of the most common kind. Okay, okay, and so in a liquid, let's say vapor phase transition, right? Uh, is the pressure fixed and is the temperature fixed basically? No. So I can boil water in atmosphere, right? The pressure is atmospheric pressure, and the temperature it will only boil when it is 100 degrees centigrade, etc. At least when it is free in the atmosphere, etc. In a cooker, it may boil earlier because of larger pressure and so on. Okay. Okay. So this liquid vapor phase transition happens to be an example of what is called the first order phase transition. Okay. Now, this kind of transitions, I have a lot of thermodynamic variables, right? So PV, let's say, or PT, right? Okay. So the left figure is in terms of PV, and the right figure is in terms of P and T, basically. Okay. So the right figure, the V label is wrong actually. Okay. It should be PT. As I increase the temperature, what will happen? I think. Okay. So let me just quickly check. Okay. Yeah, PT actually. Okay. Okay.
Sir, could you zoom in a bit?
Yeah, we can make it larger for sure. Yeah.
Thank you.
Okay.
So you are referring to first order as in terms of what we studied in chemistry, right?
Sorry, what is the question?
Sir, you are talking about first order as in terms what we studied in chemistry.
And what did you study in chemistry?
Sir, that first order, second order, that rate equation and that all, right?
No. So what is the criteria for, let's say, reaction being first order?
Sir, the power of power of the concentration in the rate equation.
No. It is not related to that actually. So we will immediately come after I discuss this liquid vapor phase transition. What is the criteria for classifying this as first order, second order phase transition? Okay.
Okay.
Okay. So phase transition, there are only two classifications: first order and second order. So it is not related to a power law, etc., but it will be related to the discontinuity in the derivatives of some quantities, etc. Right. So in the either the physical quantities themselves, like the specific heat, or in their derivatives, higher derivative, either first derivative or second derivative or third derivative, and so on. Okay. So if the specific is discontinuous, then we will call it first order. And if any of its derivatives is discontinuous, then we will call it second order. Okay. And we'll understand the meaning more clearly in a while. Okay. So let's look at this left plot, basically P versus V, right? Okay. Okay. So at, let's say, larger value of V on the right hand side, I have a PV is equal to CRT kind of a equation of state, right? So I am increasing V and I am calculating P. So P is inversely proportional to voltage. So I get this kind of a curve basically, right? Where I have all vapor. Okay. Okay. And then on the utmost right, I have a all liquid phase where I have somewhat similar kind of a behavior, which equation we have not studied. I do not know. Right. But depending on the pressure, the volume can, change, etc. So as you increase more pressure, or as you decrease the, let's say, volume, the pressure increases, and vice versa. Okay. Okay. But now there's a wide range of this flat curve, etc., where the liquid and the vapor phase coexist. Right. So that would be, for example, at a particular temperature of, let's say, 100 degrees centigrade, or 110 degrees centigrade, this curve will probably shift upwards or lower, and so on and so forth. Okay. So is this plot clear basically? Right. So on the left hand side, I have a all liquid, and that at some particular combination of P and TC, I start converting into a vapor. At the same pressure, I have almost a flat line, so that liquid vapor sort of coexists at the same pressure for a fixed temperature. And then of course this curve again, everything becomes vapor, and I again start PV is equal to CRT kind of a curve. Okay, so that's this diagram. And in terms of P and T, so on the right hand side plot, second plot here, where my cursor is, the x-axis is T, or in the P and T plot, it will, the phase diagram of, let's say, water will look a bit like this. Okay, so not precisely, because in the solid phase there are a lot of other complications, etc. But let's say for argon or neon, it will look pretty close to this. Okay, okay, or carbon dioxide also look pretty close to this. Okay, okay. So I have a solid phase which occurs at larger pressure and the smallest volumes, smallest temperatures, let's say, in a wide range of temperature region. And I have a liquid phase in between at relatively larger pressures, and at very less pressures I'll have a gas phase. Okay, okay. And so this initial solid gas coexistence line persists to some point, at which point I'll start having this liquid phase also. Okay, and this point of coexistence, so this point is surrounded on one side by solid, liquid, and on the other by gas, etc., is called a triple point. Okay, so this is the point in which all three phases can coexist. So that depends on if I apply very large pressure on water, etc., then I'll get to that point at a specific temperature and so on. Okay, okay. Then the liquid gas phase boundary, if you see, so if I keep increasing temperature, etc., the liquid gas can coexist, uh, right? Okay. But then there will become a point where this phase boundary will vanish. Okay. And beyond that, gas and liquid sort of become one, if you like. Okay. So there's no definite way to characterize this as a gas or a liquid. So, okay. So that's the phase diagram of a liquid gas solid, let's say, transition. Okay. Okay, and this particular example will be an example of a first order first transition, but first order in what we will see in more detail in a bit. Okay, uh, okay, okay. So yeah, okay, okay. Now remember, in the last class we were discussing this concavity of the S curve, etc., when it is plotted with respect to any other, let's say, quantity. So I had plotted in the last class with respect to the internal energy, but you can plot it with respect to the volume or any other thermodynamic variable also, etc. Okay, and the idea was that this S curve should be concave when I look from above, basically, right? And the part B, C, D, E, F was not satisfying this criteria, and that's why we had to do this construction of pulling up a tangent from point B along all possible directions, etc., and looking at the corresponding point where it sort of touches the curve, uh, again, such that the tangent always lies above the curve, basically, right? Right. And we discussed basically that this is the part of the fundamental equation curve which is unstable. Okay, and this figure is generic. Okay, and is not specific to liquid gas transition, so that is more important. Okay, so this figure I just bring to bring home this following point, that if you remember, we arrived at this figure because we started discussing that if I want to transfer some energy from point C to, let's say, point E, and we tried this and we saw that I'll keep doing this, I'll keep transferring energy from the lower energy point to a higher energy point, right? So in this unstable region of this fundamental curve, etc., fluctuations or inhomogeneities always tend to increase. Okay, so in terms of energy, we saw that I can keep transferring energy from a low energy region to a high energy region, right? And that is like increasing the inhomogeneity in the system. No, I'm making the system more ununiform. Okay, so these are called inhomogeneities, are called fluctuations, if you like. Okay, so I am increasing the fluctuations in the system, and increased fluctuations always correspond to unstable regions. Okay, okay. Now let's look at this curve again, basically, right? So if I look at the thermodynamically valid fundamental curve, then I'll have this complicated curve which is coming in the blue line till A, then till B, etc. And then at B, the derivative of entropy is discontinuous, right? I get this BHF line, And then from F again, I have this curve, etc. Right? So the first derivatives of entropy with respect to other thermodynamic variables become discontinuous at this point B. No? So that's the discontinuity we will talk about, in terms of which we can classify phase transitions as first order, second order, and so on. Okay. So the point B and the point F, let's say, no, are disconnected in the x-axis, which can be any of the thermodynamic variables, right? So the point B is a different phase, the point F is a different phase. Okay. Okay. And increased fluctuations in a system always denote this unstable part of the fundamental equation curve, right? And these are connected, by this construction of drawing tangents which lie above the plane, etc., to get the thermodynamically acceptable fundamental curve. And on the opposite sides of this, straight line that I made, B and F in this figure, etc., I have different phases. Okay, so this is the point I made in the last class also. So here we reiterate, etc. Okay, okay. So increased fluctuations would imply, unstable regions or phase transitions in the system. Okay, okay. So this was in the entropy perspective. We had some intuitive feel for what the phase diagram looks like, etc. Okay. Now you can go and ask basically from a thermodynamic potential perspective, or let's say, if I look at it from an energy perspective, with some constraints imposed by the reservoirs, etc. Right. So that gives me different thermodynamic potentials. What is happening? Okay. And the answer turns out that I can think of this in terms of a potential energy sort of a curve from your classical mechanics experience, let's say. Okay. And in the energy landscape, there are local energy minima. So there are local energy minima in the thermodynamic potentials, etc., and which will trap these different phases of the system, basically. Okay. And different minimas will correspond to different phases. Okay. So here's the schematic diagram. So thermodynamic potential along the y-axis, let's say, and one of the thermodynamic variables along the x-axis, etc. And it has this double well sort of a curve, no? Okay. And this, on the left, I have one local minima. On the other side, I have another local minima. And typically, a substance can have, the thermodynamic relation can have multiple such minimas of the system. And each of these local minima corresponds to sort of a different phase, right? Because the xj's will be different at each of these minimas. Okay. And if I am in this region, I have a different phase. If I'm in this region, I am a different phase. So my energy is, let's say, here, then, I am partially occupying both the phases. So phases coexist and so on and so forth. Okay. If I have only one phase at a given temperature, pressure, etc., then this curve will, become such that it has only one minima and so on. Okay. Okay. So then let's say, for example, now this curve, if I look at, then how does this relate to the water vapor, let's say, phase transition, etc. Okay. So here's the Gibbs free energy, because the phase transition happens at a constant temperature and let's say, the fixed pressure line. Okay. And on the x-axis, I have, let's say, the volume or the inverse of the density. Okay. Okay. So let's say I am at I start from the top, let's say T5. Okay. So on the T5, I have one global minima, right? Which is like one phase, let's say. Okay. And as I start coming down in temperature from T5 to T4, I start getting this two minimas. Okay. And then these two minimas are still such that, on the higher density, higher volume side, I have the global minima is on the lower density side, basically. Okay. So I come from T4 to T3, which are same phase, etc. And then I change temperature, the curve again shifts such that, to this green curve at T2. So that the high density minima becomes the global minima, and which persists, etc. basically. Okay. So this is an example. So the low density phase would be the gas phase, let's say, right? And the high density phase would be the liquid phase, etc. And as I am decreasing temperature, so I come down in temperature from T5, T4, T3, T1, etc. I come from sort of, let's say the gas phase to the phase of coexistence, but predominated by gas, let's say. And then it inverts at some temperature T2, such that, I have again coexistent phases, etc. But then I'll have a mostly liquid phase. and which persists till T1. And if I further keep decreasing temperature, etc., I'll start getting a curve which will have only the high density minima basically, and I'll reach a sort of a liquid phase. Okay, so these 5 points basically on this diagram on the right can be thought of somewhere lying between this liquid gas transition. Okay, so I start from, let's say, T5 and come down from T5 to let's say T3, T2, T1. And since I'm mostly showing this coexistence region, so all of these points are on this line which separate this liquid gas transition. Okay, so is this figure clear? This is an important figure actually for intuitively understanding this phase transitions. Okay, and the y-axis was Gibbs free energy because phase transitions are happening at fixed temperature and fixed pressure. Okay,
Sir, why does a minima in the potential correspond to a phase existence of a like phase there?
yeah, okay, because my thermodynamic equilibrium will be in a minima, no? Given that
Sorry.
entropy of the system is fixed, etc., right? My
Hmm.
thermodynamic variables optimize themselves such that my energy of the system will always be minimized,
Hmm.
right? That's the thermodynamic equilibrium principle.
Yeah.
So all systems tend to minimize energy, and thermodynamic potentials basically correspond to this energy with some constraints, no?
Yeah. Yeah. So that will correspond to some phase, you're saying.
Yeah, so the minimas will correspond to the distinct phases basically.
Okay. Okay. And another question, this PT diagram that you're drawing,
Yeah.
uh, so are like all points on the diagram achievable states, or is it only the
No,
points
no,
on the line?
no. All points are achievable. Precisely,
Okay.
right?
Okay.
So in the water vapor, etc., I can only have gas, no?
Right.
See, the lines are the lines of coexistence.
I see. I see. Okay.
Okay, lines are where I can have, let's say, gas, liquid phase coexisting on this line. On this line, I'll
Hmm.
have, so this side is a solid, so I can have a solid liquid coexisting.
Hmm.
Okay,
Okay.
and then I can also have solid gas coexisting if I'm at very, very low pressure, etc.
So, sir,
I see.
does that triple point will have three minimas?
Sorry.
At triple point, will we have three minimas?
At the triple point, we are likely to have three minimas. Yeah, so I have not gone below in volume further, etc. So this diagram doesn't have the solid phase. I agree. So this diagram is limited to the subset of this line basically near liquid gas transition. In fact, in the solid phase, there are more complicated phase diagrams, etc. Because the solids can also change the crystal structure on applying pressure. Okay, ice particularly is known to have a lot of different phases in the solid phase side. In fact, almost all crystalline objects have a lot of phases when you apply a large amount of pressure and so on. Okay.
Okay, sir.
So the two minimas correspond to two different phase lines, right? In the
No, no.
PT curve.
So the two minimas
Mm.
correspond to, let's say I'm looking at a point T1, right? So I draw a
Yeah.
line here T1, right?
Yeah.
Yeah. So this point will correspond to one curve basically.
Okay.
And two minimas because on this curve, I have liquid and gas coexisting. Right? Liquid and gas can coexist only when there are two minimas basically. Okay, because it costs some energy to jump from one minima to another, right? So I'll have to give this barrier height equivalent of energy so that this part goes into that, etc. So that's why they coexist. Okay, but I can, let's say, keep going up and I can go here where I have only liquid, let's say, or I can keep going further so that I have only gas basically, right? So that would be your T5, let's say, where I have only gaseous one minima. Okay. Okay. So let's come back to the classification. What about the classification? We talk about this first order, second order, etc. Right? Okay. Now I showed you this energy minima curve basically, right? So the first order transition you can almost always think of such that the two energy minimas are asymmetric. Okay, they are not symmetric. They are not perfect double well structure. Okay, so if they are not perfect double well structure, etc., then what will happen is this: you will have this dg by dxj are different in the two minimas basically, right? And dg by dxj are nothing but some thermodynamic variables. Okay, so the first order derivatives of the physical quantities are different. First order derivatives of the Gibbs free energy. Okay, so the Gibbs free energy are different in the two phases. Okay, and one
Sir,
of the sorry,
sir, dg by dxj should be zero, na?
precisely at the
In both
minima,
the minima.
precisely at the minima. But suppose I measure slightly away, etc.
Okay, okay,
Okay, sorry. So dg by dxj will be zero, but the double derivative will be different.
okay. That means here it should be double derivative.
Yeah. So this the first line should be
Okay.
the double derivative. Okay. Yeah. Thanks for
Okay.
pointing that out. So dg by dxj will be some physical quantity, right? Like pressure, heat, or something, right? Okay. And the first derivative of these physical quantities are different in the two phases, basically. Okay. So for example, if I measure CV, specific heat, which we measure in experiments, etc. So CV will show a discontinuity or a jump, basically, in experiments. Okay. So that's first order transition. And the second order transition is the two energy minimas are symmetric. So they will look alike, etc. Okay. So the first derivative of potential, of course, are zero. In fact, the second derivative of the potentials are alike, but their higher derivatives may be different, etc. Okay. So here it will turn out that the CV will look like continuous, but the higher derivatives of CV may be discontinuous. Okay, so the first derivative of CV may be discontinuous, etc. Or the third derivative of CV may be discontinuous, the fourth derivative may be discontinuous, etc. Okay, and all such higher derivatives of CV being discontinuous, that will classify as the second order phase transition. Okay.
Sir, can you explain again second order phase transition?
Yeah.
तेजस तेजस मित्र बुला लिया पहले.
Okay. So the point is the following, right? So dg by dxj, let's say, is some physical quantity, right?
Yeah. And X represent any extensive property,
Yeah, any extensive property, etc. Right? Okay. So the
not intrinsic property.
not intensive. It can represent intensive also, right? I am talking in terms of thermodynamic variable.
Okay.
The thermodynamic potential, right? For potentials, I have a mixture of intensive and extensive variables.
Yeah. Okay.
Right. So for Gibbs free energy, for example, the X can be temperature or pressure also. No. Okay. So that is the idea. Okay. So of course, the first derivative of G has to be zero. So what is written here is wrong. The second derivatives can be different, should be different, right? If the energy minimas have a different shape.
Yeah.
If the energy minimas look like this, let's say, no? Then the second derivative here and the second derivative of G will be different, basically, right?
Yeah.
Okay. So CV happens to be one of the quantities which is dependent on the second derivative of this G's, basically. Okay. So CV will have a discontinuity whenever I have a phase transition.
Okay.
Is that clear? Okay. And that is the first order, let's say, phase transition. So I am doing an experiment, let's say, and I measure the CV, right? And I am heating the sample, I am measuring the CV, etc. How much heat it takes to change the temperature by 1 degree and so on. Okay. And then I suddenly see that I plot CV and then it jumps. Suddenly it will start showing something else. So that's a phase transition, first order phase transition.
Okay.
Okay. Now second order is the two energy minimas are symmetric. They will look identical. Okay.
Okay.
If they start looking identical, then the CV will also be continuous, basically. No, CV here and CV there will start looking the same.
Yeah. I mean, you mean that minima will be identical? Means
Minima, the curves will look similar, but their higher derivatives will be different.
okay. You means The second order derivative will be 0.
Second order derivative will be same.
Okay, same. Okay.
Okay, so second order derivative same means some other derivative may be different.
Okay.
So second order derivative means what, right? The curvature at the precise bottom, no?
Yeah. Yeah.
Yeah. So the curvature at the precise bottom is equal. Okay. But if
Yeah.
I go slightly away from precise bottom, then I'll can get a different curvature, which will be captured as higher derivatives.
Okay.
Third or fourth or fifth and so on, right? But the third derivative of G implies the first derivative of the CV. No, sorry.
Okay.
Right? Yeah. So the derivatives of CV start being different basically. Okay. So I measure CV, I'll see that CV is continuous, but will start showing a jump or some sort of a curvature change and so on. Okay. So then I can
Okay.
start plotting the derivative of CV. And I'll start seeing discontinuity there. So either in the first or second or third and so on. So those are like higher order phase transitions. And all higher order phase transitions are just called second order phase transitions.
Okay.
So that's a stupid nomenclature, but historically we first thought that all other phase transitions are only second order, etc. And then we kept discovering other phase transitions, higher order, etc. And then the point was, there's no point of classifying them according to the degree of discontinuity of the CV. So let's just call CV is continuous first order. Sorry, CV is discontinuous as first order, and CV is continuous as second order.
Okay.
Okay, yeah, okay. So the main idea is that in first order, let's say phase transitions, the physical properties on the two sides themselves are different basically. Okay, and in the second order phase transition, the physical properties on the two sides may not look very different and so on. Okay, and second order phase transition, the common example is this icing model, etc. Let's say. Okay, so CV will be continuous, but it may have a kink. Okay, but the derivatives of CV are likely to show the discontinuity. Okay, so you can almost unequivocally think of this first order and second order in terms of this CV. CV is discontinuous first order, CV is continuous, meaning second order phase transition. So either no phase transition or second order phase transition. Okay, but for second order phase transition, CV has to show some kink or something, some behavior slope changes or something basically. Okay, so that the higher derivative will be discontinuous. Okay, okay, so that's your phase transition. Then of course the thing which is associated with the phase transition is this entropy change. So the different phases can have different entropies, right? So here we have an example from, let's say, the liquid phase. Capital S is the extensive entropy, which I can divide by the number of moles to make it the intensive entropy per mole, let's say in the liquid phase. Similarly for the so the notation is wrong. So S solid, right? So S in the solid phase, S should be here basically. So entropy per mole in the solid phase, etc. And the idea is that the entropy changes, right? So the entropy, if you remember our this ABCD curve basically, so I jump in entropy from one phase to the other. And entropy change is always at the same temperature, is always accompanied by a heat change, right? So in jumping from phases, etc., I need to supply heat to a system, etc. And in this particular example, it is called the latent heat of fusion, and which is defined as, latent heat of fusion L of LS, liquid solid transition, is equal to T times the final phase minus the initial phase basically. So in going from solid to liquid, I'll have to give energy to the system. No, we know from intuition, etc. So that's the latent heat of fusion, which is defined as heat required to convert 1 mole of the solid to the corresponding 1 mole liquid basically. Okay, okay, and similarly you can define these quantities for other things also, right? uh, okay, so I'm not able to jump. Okay. Yeah. Right. So similarly, we can define this transition for vaporization from liquid to vapor, which is called latent heat of vaporization, or from solid to gas directly at very low pressures and so on, so which is called latent heat of sublimation. Okay. Okay. So that's the second thing I had to say. And then we saw this lines of coexistence of phases, etc. Right. So particularly the liquid gas coexistence line, let's say. Okay. So you can derive an equation for that liquid gas coexistence line, and that equation is called this Clapeyron equation. So the idea is pretty simple. So if I take this PT phase diagram, I have this coexistence line, let's say, and I have point A on the gas side, on the liquid side, and A prime on the gas side. And a little away from it, I have this point B on the liquid side and B prime on the gas side, etc. Then of course, phase existence. So both the phases, liquid and the gas phase, exist in equilibrium, etc. Right? So at the corresponding point, the chemical potentials have to be equal. We already saw this, right, in equilibration when I have two or more species. Okay. Okay. So with that, we can combine to write that mu b minus mu a is equal to mu b prime minus mu a prime. So the difference of the between the two chemical potentials on the same sides are sort of equal. Okay. And then of course, for PT constant, etc., I can write delta mu is minus S dt plus V dP. No? Right. And using this, you can immediately get this equation dP by dt is equal to the entropy change divided by the volume change, etc. And entropy you can express in terms of the latent heat, etc., which is an experimentally measurable quantity, because entropy I do not know how to think of experimentally, and latent heat is I can measure. I have tables for different solids and different transitions, etc. So I immediately get this equation dP by dt is equal to L by T delta V. Okay, and this equation gives you the equation for this curve, basically line of coexistence for solid gas phase actually. Okay, so that's all I had to talk about today, and we'll stop here. Okay, any questions?
Sir, I didn't understand the last line.
This one, latent heat.
Yeah. Recall that del mu equals to from this and the line after. How it came? I didn't understand.
So we had this equation, right? Delta mu. So mu b minus mu a is delta mu, right?
Yeah.
Right. So delta mu is this. So I write this S on one side times dt. So on this line, I have the same basically dt, right? Between A and B,
Yeah.
on both sides, I have the same dt and same dp. But I have different S prime and V
Okay.
prime, right?
Okay.
So
That
I
means
just take,
you have equated delta in A point with delta in B point, I think.
yeah. So I just did basically delta mu on, let's say, the liquid side is equal to delta mu on the gas side.
Yeah. Okay.
Right. So I'll get an equation
Okay.
like minus S prime dt plus V prime dp is equal to S dt plus V dp. Okay. And that immediately gave me this equation.
Okay.
Okay. Any other question?